So let us start where we have left. So in the last class, we were looking at the software aspect of control system engineering, and we looked into MATLAB and Scilab. So I have a TA named Yogesh Singh. Yogesh Singh. He is doing his PhD from IIT Gandhinagar, and he is a PMRF fellow. So Prime Minister has chosen probably 100 or 200 potential candidates, and they used to give stipend to these guys in order to promote higher education. So he is one of the guy, and he works in control systems, and he is going to help me out as a TA work in this particular course. Okay, so whatever the MATLAB and Scilab from now onwards, he will give you guys a tutorial session in between whenever you guys need it. Okay, I will coordinate. In this particular class, we are going to start with a new chapter. Chapter 1 was introductory chapter, and in this chapter we will look into the chapter name is mathematical modeling of control systems. Okay, we'll start with an introduction what mathematical model is all about of a real physical problem. Let's suppose you have a car, or you have an aircraft, or you have a falling pen. Okay, not only falling pen, anything, you strike your ball with a bat, or you're falling from your roof or chair, you are closing the lid of the laptop, you're working on mouse, everything, every dynamical system, any moving system can be modeled by some mathematical equations or some differential equations, or maybe ordinary or partial differential equations. So those set of equations uh, are called as mathematical model of the real physical problems. So next we will talk about the Laplace and inverse Laplace transform. Okay, the mathematical models are often hard to solve. Okay, that is why we will take help from this mathematical construct called Laplace transformation. Obviously we are not going to solve it, but we are going to seek things in the framework, output to input.
Screen is not visible.
Okay, I'm sorry, let me keep to share that. Sorry. Now is it visible?
Yes, sir.
Okay, so I think we have not left anything that is not shown. Okay, so introduction. Yes, we are talking about the Laplace and inverse Laplace transform. So it help us to transform our time domain equations into the complex domain, or so to say S domain, also called Laplace domain. Okay, and the reason to do this transformation is in complex domain we can do certain algebras more easily than the time domain. Okay, analysis, and once we have done with our algebraic manipulations, we can switch back to time domain again by means of inverse, something called inverse Laplace transform. Okay, and we'll look briefly, we'll look in the subsequent slides itself how easy it is, to do these sort of transformations. Next we will talk about the transfer function. So all my physical systems that I make in in the form of mathematical model are essentially can also be written in the form of transfer functions. All mathematical equations or modeling, mathematical or physical system, can be written in terms of transfer function. Transfer function is nothing but the ratio of output response to input response. Okay, how much forcefully you hit a bat or a ball, and how far it went. Okay, it's kind of input, you are giving a force to the input, and how far it has reached, its output. So the output response to the input response is often associated with the transfer functions. Obviously we take our initial conditions set to be 0. All sorts of technicality we will look into in the details in the latest slides. We'll also look into the impulse response of any physical system. Impulse response means you it is a very intrinsic uh, way to analyze the any physical system. If you are going to do an impulse and how it behaves. So this is also quite uh, widely used technique to analyze the system, all sorts of physical systems that we look into. We will also look into some of the block diagrams, although we have also talked about some block diagrams in the first chapter itself, but we'll also look into it. Then we'll look into we'll talk about open and closed loop systems in the framework of transfer function, in the framework of transfer function, or in Laplace framework. Okay, we'll also look. And lastly, this comes under modeling of state space. There is something new I will talk about. There is a way, or there is a mathematical construct in which the models can be the physical systems can be modeled uh, in the framework of modern control techniques. Modern control technique. So all these things are essential for classical controls, classical and modern control. But this is exclusive to modern control theories. And yes, we'll also look into briefly into how we are going to make a state space model from a physical system. Okay, let's first talk about the mathematical modeling of any dynamical system. So let's first define what mathematical model is. A mathematical model of a dynamical system is defined as a set of equations that represents the dynamics of system accurately or less fairly well, at least fairly well. So as an example, there is a car shock absorber. So this is a car shock absorber. You have a wheel, you have a damper, you have a spring, and your car chassis is on top of it, and on that chassis you are sitting over it. Okay. And in order to get you a comfort ride, this car absorber model is designed in certain way in order to give you a comfort ride. And this physical real problem can also be uh, fairly represented in this sort of lumped system parameters, or you can say spring mass system, spring mass damper system. Okay, it can closely mimic what behavior that your real shock absorber will show you. You can actually fairly approximate by a generic spring mass damper system representation. Okay, and we will actually go into the details of these all sorts of spring mass damper system, whether you have two springs, five springs in series, dampers in parallel, all sorts of, there might be 2, 3, 5 masses. How to make a mathematical model out of it, then how we are going to control it with the applied control techniques in the later chapters. Before moving into uh, understanding of the Laplace transform and system modeling, we in this particular course we will be sticking towards few assumptions. Okay, so this whole course are based on certain assumptions, and those assumptions I will uh, note it down in the following way. The first and the foremost assumption we will be taking up in this particular course is we will take up the all the systems as a linear system. We are not going to talk about non-linear systems in details, and the reason being, linear systems, I mean the approximation of linear non-linear system to a linear system uh, is fair enough to give us a notion of the real physics out of it. I mean, no need to go into the complex behavior of non-linearity of the system. Just being in linear framework, we can actually fairly accurately we can mimic the system in mathematics as well. Okay, no need to go into the non-linearity of this. Obviously, if the your system is complex, such as your aircrafts, where your safety and all sorts of things are there, so you should go and do the non-linear control. Um, you should do the analysis in non-linear control framework itself, where the safety and the accuracy is concerned. But in this particular course, we will take up things in linear framework only. And the system which belong to linear systems are those systems whose mathematical equations have either constant coefficients or the function of independent variables only. Okay, this is kind of mathematical glitch, but just to give you a feel of what exactly I'm telling, so let us talk. Let us talk a simple system as a spring mass system. So you have a spring K, you have a mass M, okay, and I'm applying a force F on this mass, and because of this force, this mass acquires an acceleration A, and this acceleration can also be written as d2x by dt square in terms of displacements, and displacements is written in this coordinate from here, okay, from the equilibrium mean position. Now I can make a now I can represent this this physics, this force application leads to acceleration. I can write as F is equal to mass times, so net F, okay, net F is equal to mass times acceleration d2x by dt square. d2t by d2x by dt square can also be written as x double dot in most of the literatures. So double dot sign means twice it has been differentiated with time. One dot means one time it has been differentiated. Here it will take double differential. So net F, what is the net F you can expect here? So let me do the free body diagram analysis here. In free body diagram, you take this mass as a point mass. Okay, this is as a point mass. You apply a force here F, it has acceleration A, and because of the displacement, this spring elongates, and the force that a spring possesses is minus k times x, minus k times the displacement. I mean, it is proportional to its displacement, minus or displacement. So it will act in the opposite way. So kx would be the opposite force, spring force that will be applying on at any time. Okay, so here I can write net F is equal to F, this F minus kx is equal to mx double dot. Okay, so I can write mx double dot plus kx is equal to F, and yes, that's it. This is your mathematical model of any generic spring mass system. Okay, you apply a force, this is your input, and you are getting some displacement x. So okay, So input by output, any input by, I'm really sorry, this is your output. Output is your displacement. So for any input, you can have your output. Okay. So essentially it can also be written in terms of Laplace, transfer function. We'll look in the subsequent slides how it has been written uh, in, in the way of transfer function domain. Okay. So here we are talking about linearity. Okay, so this particular system is a linear system. The reason being, if you write in terms of differential equation d2x by dt square plus k times x is equal to f. So you can see all the coefficients here 1. So all the coefficients are either constant or this is also constant. Okay, or it's a function only on independent variable. So independent variable is what? So dependent variable are here are x. Can somebody tell me what is independent variable and what is dependent variable? Any of you? Poonam madam might have taught you these things, or mathematics uh, faculties might have taught you this. So you guys know the classification: linear differential equation, nonlinear differential equation, quasi-linear differential equations. Anybody? Okay, let me tell you here 1 and x are multiplied with the dependent variables. So x will be the dependent variable. X is dependent variable. And time here is independent variable. If the equation would have been something like this, d2x by some other real physical scenario as d2x by dt square plus 2x times x. Okay, or you could have multiplied x over here also, x times d2x by dt square times 2x, or so 2 is fine, but here x is multiplied with the dependent variables. The dependent variables are multiplied along with it. So this equation is essentially a non-linear equation, and we are not going to take up these sorts of non-linear equations in our control framework. Okay, we are going to take up only linear equations in this whole course. In the whole semester we will be goofing around the linear systems only. Okay, the next assumption I will take in this whole course is I am going to take up the things as a linear lumped parameter model. So lumped means, what do you mean by lumped? So what I believe is this mass that has been attached to this spring is not, it's a point body mass. Okay, all the masses are concentrated on a single point. Okay, it's not like that it has some moment of inertia or it has some orientation so that it would affect not only its um, acceleration or uh, angular acceleration also. Okay, so it would be lumped in some sense. Okay, it will be lumped in a point body. Okay, so and that is also a valid assumption as long as we are going to seek low frequency operations. Okay, we are going to seek low frequency. So let's suppose I am exciting this spring mass as sine omega t with some forcing frequency sine of omega t, where omega is the forcing frequency of the input force, some oscillatory force I am talking about, some omega, some 1 radian per second. Let's suppose I'm oscillating it with. So as long as this omega is in the low ranges, this lumped parameter model is valid. Otherwise, if we were talking about very high frequencies, then this lumped parameter would not be valid, and we will not take up those sort of cases in this particular course. So with the start of this course, I will I want to make sure that we are going to take up only linear systems. We are going to take up only loved parameter models, and also the last assumption that we'll take up is the principle of causality. Okay, and what is this? It applies to a system. This means that the current output of the system, the output at time is equal to 0, depends on the past input. The input for t is less than 0, but does not depend upon the future inputs. Okay, so what it tells is, it is quite trivial to understand. It is quite trivial actually. So what it tells is, I am going to push this particular mass with some input at t is equal to, let's suppose t is equal to 0, then I would talk about the displacement of this particular mass at t greater than zeros, not the previous time steps. Okay, so that this is trivial also. We will also, I mean, this is nothing more to say, but yes, we will stick towards the principle of causality as well. Okay, linear system I have already talked about. A system is linear if the principle of superposition is applied, or in physical sense, it states that the response produced by simultaneous application of two different forcing function. Let's suppose this is spring has, I'm giving some force. This spring is pulling with kx. It has some acceleration. So what this principle of superposition tells, that if I would have given f1 input and it produces some response, if I would have given f2 input, it would have given some response. Okay, then if I would add these two forces, f1 plus f2, okay, then it must give a response that is the algebraic sum of responses of individual forces. So only this, I mean, only this way the principle of superposition is valid, only when the system is, your system that you construct was a linear system. Okay, so this is a more realistic way to see how the principle of superposition uh, works in an experimental investigation of dynamical system if cause and effects are proportional, thus implying that the principle of superposition holds. Okay, what would have this mass would be a function of time. Let's suppose in your aircraft. Okay, so your aircraft is flying, and the aircraft actually, it has its own mass, that is its dry mass is capital N, but almost 40 to 30 to 40% of its mass constitutes with its as its fuel mass, and this fuel mass is actually decreasing with time. Okay, so when you are going to make a model of it, then your mass that is sitting over here, so our mathematical equation for spring mass transfer system was F is equal to mx double dot plus kx. So m sitting over here is no more constant for an aircraft flight. Why? Because mass is actually a function of time now, and now this complicate things and give rise to non-linearity in the system, and thus we are not going to look into these sort of complex sort of problems in this course. Okay, so just keep in mind all the coefficients should be of constant coefficients, and the principle of superposition should be applied on it safely, and we will take up only those sort of systems in this particular course. And just now what I have told you here is that m is a function of t makes the system not a linear time invariant system. And this is the last assumption we will take up in this course, that all the systems will take up it as linear time invariant system. Your intrinsic properties such as mass, your spring constant should not be a function of time, so to say. Okay, and thus make things, our life easy to solve. Although this may capture real physics or not, that is of another concern, but in terms of solvability, we will restrict ourselves to linear time invariant systems, such as its intrinsic properties such as mass, momentum, or any sort of thing is should not change with time. Your whatever the matrix you have chosen is it's not a function of time. Okay, so this was the last thing, and yes, now we will move into uh, understanding the transfer function, because the transfer function is actually your your plant or model in Laplace domain. Okay, your plant was f is equal to mx double dot plus kx. This was essentially in time, and we are going to transform this equation into Laplace domain or in S domain, and then we formulate output by input ratio of in S domain, and we call this as transfer function of uh, the system. Okay, so before understanding transfer function, I've told one a new keyword, that is Laplace domain or Laplace transformation. So let us first understand what Laplace transformation is all about, and what is the significance of doing that. So let me go back. So Laplace transform is a mathematical construct, and it actually, let's suppose you have a function f in time domain. Okay, any function, you can think of any function with time. Either it can be constant, it can be parabolic, or any polynomial, or any function in time, continuous function, can be transformed into f of s by applying a operator over it, which we call as Laplace operator. L. Okay, and what is that operator? So this operator says that whenever you see any function, okay, so don't have to worry about the most of the integration signs over here. You have nothing to do with the complexity of this Laplace transformation. You just have to uh, see this table and how these things works beautifully. You will see in a while. So whenever you see any function, what you do, you multiply it with e to the power minus st, and you integrate this function dt from 0 to infinity, and whatever value you will get is actually your transformed function into Laplace domain. So here what you do, you take up things in time domain, okay, and you multiply it with e to the power minus st. This is how it is done. I mean, one mathematician came and he did some mathematical uh, glitches, and he told that fine, whenever you do this, you multiply with e to the power st and you integrate with dt from 0 to infinity. Whatever the thing you get is called transformed variable in Laplace domain. This is your S domain or Laplace domain. Now the advantage of doing that is, uh, in control system engineering, when you do any sort of algebra in time domain, it will be tedious and you cannot do it by hand. So some mathematician, maybe Laplace, I have to check, maybe some guy came and he told that okay, there is a beautiful way to do some algebra or manipulation in Laplace domain. If I do this, I'll get time domain converted into Laplace domain, and then I do all sorts of algebraic manipulations, and I'll switch back to my time domain again in order to get the final result. Okay, this is just a mathematical glitch. No need to worry about this whole equation. So see, you have ft e to the power minus st से आप multiply किए dt 0 to infinity, and what you get is fs. Okay, no need to actually do that. So let us suppose I take my ft as a constant 1. This was my function. So let's suppose this is my t, this is my ft. So I have a constant function, linear function. This is 1 throughout. Okay, now I want to transform this into Laplace domain. So what I do, so I will integrate my ft with e to the power minus st dt 0 to infinity. So what I get equal to ft के जगह पे 1 लिखिए 1 e to the power minus st dt, and if you do the integration properly, you will get 1 upon s. Simple. Okay, so all sorts of tabular form. So if it would have been x, so let's suppose it would have been x, your ft was some function, sorry, ft was not x, ft was t. Okay, then I want to transform it into Laplace domain. So fs is equal to what? T times e to the power minus st dt integration 0 to infinity, and it usually reaches to some, I don't know, maybe some s plus, maybe I have to check. So in order to do that, what we do, we go to the textbooks and we see table number A1. You have all of you have Ogata textbook. Okay, modern control engineering. Go to the appendix table 1, see table 1. So all your FTs are converted to FS. Okay, and there is a tabular chart that is being given. So unit impulse, whenever you do the transformation of unit impulse, I'll talk about what it is in later classes. You will get 1. If you have 1, this function I have taken ft is equal to 1, and what I got, 1 upon s. This is my fs. Okay, whenever I took t, so my ft was t, and when I do the integration t e to the power minus st dt 0 to infinity, when I do proper algebra, I'll get 1 upon s square. Similarly, all sorts of informations are given, t to the power n, t to e to the power minus at, which is widely used whenever you see this function e to the power minus at, your ft is e to the power minus at, and you can get the fs as e to the power minus at e to the power minus st dt, and when you do it properly, you will get 1 upon s by a. Simple. Okay, so all trigonometric, all exponential, all logarithmic exponentials are converted back into very simple algebraic sense, and which is easy us to do the analytical, easy to handle analytically, right? So when we have sine omega t, as my f of t was sine omega t, so when you do sine of omega t e to the power minus st dt 0 to infinity, you will get fs as omega by s square by omega square. See how nice and easy things came. Similarly, so far we have talked about Laplace transformation. This particular mathematician came up with this, that you can actually switch back here and there by you can switch back to time domain from Laplace domain by doing inverse Laplace transformation, and you don't have to worry about this big integration sign over here. You just have to put my fs here, multiply it with e to the power st ds, and ds should go from one complex domain to, from minus infinity complex domain to plus infinity complex domain, and times 1 upon 2 pi complex number. And you don't have to worry, don't go into the details of it, what it is telling. Just remember, whenever you see fs, so let's suppose I take fs as 1 upon s, right? We take, let's suppose, 1 upon s, and I take 1 upon s, so fs is 1 upon s, right? So when I put here 1 upon s, so times e to the power st ds, ds, and when I do, you don't have to do it actually. When you do it properly, if you know the integrations and all sorts of complex integrations, you would do from minus I infinity to c plus I infinity 1 upon 2 I pi, and if you do it properly, you will get things as 1. Okay, transform back to 1, and this is in time domain, and you will see 1 upon s is transformed back to. So this is an exhaustive table or chart. You can actually make a use of whatever time domain things, you can switch it back to s domain. Whatever s domain thing, you can switch it back to time domain. Now let us take one quick example. You guys take a paper and pen, and here is my fs as s plus 3 by s plus 1 times s plus 2. I want to take an inverse Laplace transform. So inverse is written as L1 minus 1 f of s. I want to estimate this is equal to what. So essentially inverse Laplace transform of fs gives me f of t. So I want to estimate this function. What is my ft actually? So can somebody do this for me? And how can we proceed? Akash Ojha, are you there? Akash Ojha. No, yes. Adit Patel. No, you guys are not listening.
Yes, sir.
Okay, so Adit Patel बोल रहे हैं.
Yes, sir.
Okay, यहाँ पे हम क्या करें बताइए. हम
Sir,
कैसे
we
करें?
can
हमारे
try
पास टेबल्स. हाँ, partial, very nice,
partial
very
fraction.
nice. Partial fraction, very nice, good, good, good. So s plus c, तो कैसे करेंगे बताइए, तो थोड़ा हेल्प कीजिए मुझे नहीं आता है अगर, तो बताइए.
सर ऊपर नीचे 2 की मल्टीप्लाई करेंगे.
2 की मल्टीप्लाई करेंगे, या फिर हम ऐसे
या
करते हैं, हम
इन्फिनिटी
मान लेते हैं. Okay, let's do this way. Okay, there is a good way to do this. So what I want to do is, thank you Adit, you are right. So we have to do the partial fraction here. So what I do, I will tell that this particular numerator and denominator, this fraction can be written as a by, I want to write it as a by s plus 1 plus b by s plus 2. Okay, nothing to worry about. And now by equating the coefficients, I will estimate my a and b. Let's see how. What I will do, I will take s plus 1 times s plus 2. This is my LCM, and this would be a times s plus 2 plus b times s plus 1, right? Sorry. So this is my as plus this is my bs, right? And plus 2a plus b, isn't it? Divided by s plus 1 s plus 2. Okay, and this would be s common, a plus b plus 2a plus b divided by s plus 1 s plus 2. So now I will equate things from left hand side to right hand side. So equating, I can see the coefficient of x is 1. So the coefficient of here, this would be equal to 1, and the coefficient, I mean the constant is 3. So this particular guy would be 3. So I know that a plus b is equal to 1 and 2a plus b is equal to 3. Now I will do minus. So a is equal to 2, that's for sure, and b is equal to 1 minus 2, that is minus 1. Okay. Okay, now we are in the shape. So let's, so what I will tell as fs is equal to uh, s is equal to a by s plus 1. So a is my 2 by s plus 1 plus b by s plus 2, right? Now I will go to the table. So टेबल में जाते हैं. So s plus 1 कहीं दिख रहा है आप लोग को, बताइए तो.
पीछे पीछे
हाँ, यहाँ पे s प्लस ए दिख रहा है हमारा, ठीक है. तो जैसे ही हम देख रहे हैं s प्लस ए यहाँ पे है, s प्लस सम a मतलब 1 2 3 4 एनीथिंग, आई विल राइट दिस एज e raised to the power minus 80. Okay, so what I will do here is when I do the Laplace inverse Laplace, so inverse Laplace of fs is equal to inverse Laplace of 2 by s plus 1 plus inverse Laplace of, sorry यहाँ पे minus 1 by s plus 2. Okay, and 2 will be out here, so 2 times e to the power minus t plus, और माइनस साइन अगर बाहर निकाल ले तो माइनस e raised to the power minus 2t dt answer. Okay, now quickly I will show how you can do it in MATLAB also. Just bear with me in 2 minutes. MATLAB also I'll see how far I can reach. So just 2 minutes I'll take. I'm joining from my laptop, so let me, okay, you guys are able to see my screen?
No, sir.
Just let me know. Okay, just 2 minutes, bear with me. Now?
Yes, sir.
Okay, good. So now what I do, I'll show it how to do this in thing in MATLAB. So this is your MATLAB. MATLAB, are you able to see in MATLAB?
Yes, sir.
Yes. Okay. So see. So what was my function? Can somebody tell me quickly?
S plus 3 upon S plus 1 into S plus
Okay.
2.
So okay, thank you. So what I will do, I will quickly write. First, I will call the function. So there is an inbuilt function sims. So I'll tell you in later classes how why I have written this. So sims s. Okay. Let me do this. So let me define my f. F is equal to uh, s plus 3 यही था divided by s plus 1 times s plus 2. ये था क्या, कोई बताइए?
Yes, sir.
ये था, ठीक है, इसको हम एंटर करते हैं. ओके, आई एम रियली सॉरी, कुछ तो गड़बड़ हुआ है. ओके, मेरा यहाँ पे ब्रैकेट छूट गया. ठीक है, एक ब्रैकेट छूट गया. देखिए ये सब चीज़ ध्यान रखना है, ब्रैकेट वगैरह सही रखना है. तो जैसे हम करेंगे सी, उसको वो ले लिया एस प्लस 3 बाई एस प्लस 3 सॉफ्टवेयर ले लिया. अब ठीक है, अब मुझे क्या करना है, इनवर्स लैप्लास करना है हमें. ठीक है, आई लैप्लास of capital F. I'll do that. Just hit enter. Okay. I made a spelling mistake. Lap.
You have written Laplace.
Laplace. So see, when I do, I'll Laplace. Let's see. So see, answer is 2 e raised to the power minus t minus e raised to the power minus 2t, which is equal to what I have derived. See how easy it is. So every time you stuck with your hand calculation, you have MATLAB, you can just verify it and you have the answer. So you don't have to go into the details of those analytical glitches that you might come across with. So whenever you are stuck, start MATLAB, start doing it. Okay, with this I don't want to go far. So any doubts so far in this class? Anything?
No, sir.
Because these are the building blocks, these are the starting steps. Because once I reach certain level, I will not be doing this micro mathematics and micro MATLAB with you guys. Okay, I'll just start putting some functions and so अभी जितना पूछना है पूछ लीजिए, ठीक है, क्योंकि बाद में और क्विकली चलेंगे हम लोग. ठीक है, फिर जितना अभी बताएं उतना में अगर प्रॉब्लम नहीं है तो फिर हम लोग लीव कर सकते हैं. ठीक है, कोई एक मिनट, एक चैट आया है, देख लेते हैं क्या है. How to do this in Scilab? Okay. So what I will suggest is this TA will be taking a tutorial on everything. One hour tutorial I will keep for him, and he's good in these things. He's also good in these things, so he will help you out. And whenever you want to do things in Scilab, you can just Google what is the thing you should do to take the Laplace transform, In Scilab, you will get the proper function names and you can do it right away. Okay.
ओके सर.
ओके, उसमें भी हो जाएगा, उसमें भी कुछ ज़्यादा परेशानी नहीं होगी, आराम से हो जाएगा. मैटलैब में दिखा दिए, उसमें सेम चीज़ होता है. उसमें थोड़ा सा मे बी फंक्शन का ऊपर नीचे होगा 19-20, उसका मे बी उसका तरीका डिफरेंट होगा थोड़ा सा, बट मैटलैब वाइडली यूज्ड है इसलिए क्विकली बता दिए. शायद मुझे भी देखना पड़ेगा अभी. ठीक है. ओके, अगर नहीं होता तो फिर पूछिए, मैं बताऊंगा नेक्स्ट क्लास में. ठीक है, आप लोग खुद से ट्राई कीजिए. ठीक है, छोटे छोटे प्रॉब्लम्स करना शुरू कीजिए. ओगाटा को आपका गॉड बुक है, ओगाटा कंट्रोल सिस्टम्स का, उसको पूरा का पूरा फॉलो करना है लाइन बाय लाइन. ठीक है, जैसे हम लोग थर्मोडायनेमिक्स में सेंजल फॉलो किए हैं, यहाँ पे हम लोग ओगाटा फॉलो करेंगे. फाइन, लेट मी टेक द अटेंडेंस. And today I am not going to give attendance to Akash Oja. Okay. Okay, bye then. We can leave then.
Thank you, sir.
Thank you.